In this video, I want to look at the intersection of three planes, but here I'm going to look at the specific examples where there's no intersections or no lines of intersection between the three planes at all in space. So none of the planes will intersect one another at all, whether it's two planes at a single line of intersection, or all three planes at a point or a single line of intersection, or single lines of intersection. So the planes don't meet each other at all. Looking to figure out what this is and how we deal with it. Now in this sort of scenario, there really is only two possible outcomes and two possible setups that we can be dealing with. If there's no intersections between the three planes, what they either are is coincident on a plane of intersection, so they're all the same plane, or there's no intersections at all and all three planes are parallel. So they coincide with one another, they all lie upon the same plane, they're maybe just multiples of each other and bigger or smaller in terms of size. There's no intersection at all, three planes are parallel, they never touch each other. In either case, there's a set of steps that we have to do, and again, as with the others, we have to use elementary row operations on our augmented matrix, and we determine one of two scenarios. Two full equations cancel out and are redundant, so zeros in all of those two equations. If that is the case, then it's a plane of intersection and the three planes coincide with one another. Or two equations cancel out to a point where we cannot get a solution to them. And if we cannot get a solution to them, then all three planes are parallel. There's no solution that satisfies even a pair of the equations, let alone all three. So I'll show you an example of these and actually how straightforward it is to do the calculations. So first one, I want to determine the intersections of the three planes given here. Now the first thing we do is we set up our augmented matrix with all the coefficients and parts of the equations in it. So first row will be 2, -1, 3 and 4. Then 6, -3, 9 and 12. And then 8, -4, 12 and 16. Now, if we do elementary row operations, if I look at it, I can say, right, so I'll do row 3, take away 4 of row 1, and I'll do row 2, take away 3 of row 1. Now, if I was to do that, what I'd end up with is my top row would stay the same, 2, -1, 3 and 4. But my other two rows, what would happen to them in this case is they would completely cancel, and I'd get two rows full of zeros. So what that means is there's two redundant equations, i.e. two equations that are multiples of the other equation, so don't play into it. So what that means in this one is that they coincide, i.e. all three of them essentially are the same plane, just different sizes. Alright, so they're all lying on top of each other, so you may have, let's imagine this is the third plane, there's my second plane there, and that might be plane 1 in terms of the equations. But they're all lying on top of each other, they're just bigger or smaller, depending on whether we've scaled them up or down using the equations. So they coincide, job done. Second example of them, determining the intersection of these planes here. Again, first step, set up your augmented matrix. So in this case I've got 4, -8, 12 and 12. I'll have 2, -4, 6 and 2, and I'll have 3, -6, 9 and 6. And again, what I can do is elementary row operations in order to eliminate some of the rows and variables, some of the rows and numbers, sorry, and see what I get. Now if I do row 3, take away 3/4 of row 1, what you'll notice is every element in row 1 is divisible by 4, so this 3/4 of row 1 is actually not going to give me something that involves fractions. It'll all be nice whole numbers, and I can take them away, and I can similarly do the same thing here. If I do row 2, this time though, take away half of row 1, I'll then get the same idea. It will still be whole numbers because they're all even, and I can take them away and start to eliminate terms. If I were to do that though, what I'd end up getting is my top row would be 4, minus 8, 12 and 12. And my second two rows, the x, the y and the z, would be 0 for each of them. But my variable at the end would be negative 4 for the second row and negative 3 for the third row. So what that means here is that I've got two inconsistent sets of equations given by here, because essentially the second row tells me that 0 is equal to negative 4, and the third row tells me that 0 is equal to negative 3. So I've got two inconsistent sets of equations. So in this one here, there is no set line equation or point that will satisfy all three planes or even a pair of the planes. So there is no line of intersection between two planes or three planes. There's no point of intersection of all three planes here. And if I look at them, they're not parallel to each other. Sorry, they're not coincident. They're not scalar multiples of each other. So what that means is in this case, all three of them are parallel. So that's the big difference between this one and the previous one. So that's the big difference between coincident planes and parallel planes. Coincident planes will give me two redundant equations, so total rows is 0. Three parallel planes will give me two equations which are inconsistent, i.e. cannot be solved. And that lack of solutions implies a lack of intersections, so they must be parallel. For these ones here, it's quite straightforward to notice and do the calculations. Whenever we're looking for intersections of planes, it always follows the same set of steps. First thing we have to do is set up that augmented matrix and then do our elementary row operations to start eliminating terms. As we do that, we'll start to determine which of the scenarios and the setups it will be that we're going to get an outcome of, i.e. all three planes intersecting at a point or one line, the three planes intersecting at pairs of lines, or absolutely no intersections at all. Following the steps and the calculations, this is a straightforward technique to use. It's just lots of numbers and a bit of jiggery-pokery, but hopefully your algebra skills and your numeracy skills will be up to it for that.